Today I want to show you how I went about solving problem number 2, gridlock, found here on the Solidity Challenges repo. In order to get started, simply clone your repo and open it up in your preferred editor. Once you've done that, navigate to the README file. The README for gridlock states that the contract is amassing a significant amount of ether, but rumors suggest it harbors a critical vulnerability. Exploit the contract, improve your skills. Success means rendering it unusable. All right, so that's the takeaway. Let's just make it unusable. So like a DOS attack. Right. Looking at the gridlock.sol, we can start from the top down. It's a pretty small contract. They give us a state variable called total deposited. And when we deposit, it just requires that the value that we pass be greater than 0. And if it is, it'll take that value and it will add it to the total deposited. Okay, straightforward, makes sense. Then it has a withdraw all function and looks like 2 getters. Let's ignore the getters because you can't do anything with those. And withdraw all. So with this one, they have an assertion right off the bat here that the balance of this contract must equal the value found here in total deposited. If it does, then they're going to reset that value and they're going to send the balance of this contract to you, message.sender. All right. So I think we found our exploit point here. This only works if this is true. If it's false, then the withdrawal can't go through. If it can't go through, funds are locked, denial of service, contracts rendered unusable. So the question becomes, how do we make this false? How do we make a difference between the balance of the contract and the value found here in the state variable? Okay. Well, we know that in order to add value to this variable, we have to use the deposit, and I see no other way of doing it from that side of it. So my focus was to focus here on the contract balance. How can I increase the contract balance without increasing the value in the total deposited variable? There's a couple ways you can go about it normally, but this contract limits us. I was thinking, okay, receive function, I'll just make a call, send some value, but I don't see a receive function, so that does not work. So my approach was to use self-destruct. Self-destruct will allow me to send ether to a contract because the contract that it's coming from is about to be destroyed. So let's see that with an attack contract here. My attack contract, as you can see, very slim and lean, just imports the gridlock sol file, and in the constructor we make an instance of it. Now my attack here is simply going to call self-destruct, and it needs a target to send that ETH to. So I'm going to send the ETH over to gridlock, and then this contract will be destroyed. All right, let's see that over in the test file. So over here on gridlock.t.sol, I import my attack, and then this contract here, it just has an instance of the contract. It gives us a wallet called Challenger, deploys the contract, gives the contract 50 ETH. So that's that, what did it say here? It's amassing a significant amount of ether. So that would be that significant amount of ether right there, 50 ETH. And then the Challenger, I guess that's us, we have 1 ETH. There's a pre-check to ensure those balances are correct. And then there's a block here for us to add our attack logic. You can see my attack logic simply deploys a contract with an initial value of 1. And then I call attack. And remember, when I call attack, this single ether is what's going to be forced over into the gridlock contract, creating that discrepancy between those two values. And then it looks like in order to succeed here, we are expecting a revert when we call withdraw all. So let's go ahead and do that. Let's move over to the terminal. I've already preloaded the command. You can see right here that we deployed our new contract, new attack, and then we called attack, and inside that contract it called self-destruct, and then we expected a revert and when we called withdraw all, and we got a panic. The assertion failed. That's exactly what we wanted to see. So this one was pretty straightforward. There wasn't too much code, so you didn't get confused going off in the wrong direction. It was easy to focus your efforts, but it did give you an idea about like strict equality and the complications that can come about when using it in such a manner. Any which way, if you did happen to find a different way of going about it, I would love to hear about it. Or if you just want to talk about my approach, you can find my contact information in the details below. See you in the next one.